next speaker, also from Solaris, Dr. Alexey Maximenko, would present a tender X-ray absorption spectroscopy beamline at Solaris called ASTRA.
Thank you, Danila. Could you see my screen?
Yes.
Okay, then let's start. Good afternoon, dear colleagues. My name is Alexey Maximenko, and on behalf of the ASTRA Beamline team, I would like to represent you our beamline, which is called ASTRA, and we specialized in XAS measurements in tender and in hard energy range. First of all, I would like to thank the organizers to give me the opportunity to present the beamline, and I hope that this information will be interesting for you. So let's start from the introduction to the beamline. As Martin told you a few minutes ago, that Solaris is a quite young research infrastructure, and taking it into account, we could say that ASTRA is also a very young infrastructure. And if we compare the length of the Pollux beamline, where Kasia told you that the length of the Pollux is around 11 meters on the experimental hole, so then I can say that ASTRA is even shorter, and as you can see, it is very compact beamline, only 6 meters on the experimental hole. And the name ASTRA is actually an acronym which you can see here: absorption spectroscopy beamline for tender energy range and above. It is some kind of a sci-fi name, which is also an acronym of the technique which we are using at our beamline. But nevertheless, if the beamline is quite small, it actually a concentration of a big amount of experience from different partners who actually build this beamline. The main leader of building of this beamline is the Niederrhein University in Krefeld and Bonn University in Bonn. Jagiellonian University definitely as Solaris. Also, we have a technical cooperation with Synchrotron Research Institute in Thailand, and also a lot of technology we got from Center for Advanced Microstructure and Devices, KMD, Louisiana. The idea to build such kind of a beamline appeared in 2018. Here you can see on the photo where representative of all of the organizations signed a contract in December 2018, and already in June 2022 we opened and started our operation. Here you can see the schematic overview of our beamline. You can see it is not only short on the experimental hole and simple, but also very short and simple in the storage ring. In the storage ring, where we have only beam shutters and the fixed mirrors. In our case, we do not have any collimators or any mirrors in the front end, and on the experimental hole we have only 5 main elements, which is a diagnostic model which allows us to understand the beam profile which we get after all of this fixed mask in the front end. We have our monochromator, we have a beam shutter, and what is quite important, I would say, that we don't have any windows upstream from the monochromator. So it means that here the whole beamline we don't have any windows, and if you see here on the pressures which we have in our monochromator, which is a high vacuum device, and in the other and in the rest of the storage ring it is ultra high vacuum device. And having no window, it is quite important for us. I will tell you a little bit later about it, but helping us to keep the pressure difference between the monochromator and the rest of the rings is actually is actually the help of this device, which is called differential ion pump. On one side of this device we could have a pressure 10 to the minus 5 and millibar, and on the other side we could have a pressure 10 to the minus 11 millibar. So this differential ion pump allows us actually to have a monochromator which could work in high vacuum without any window. And the only one window which which we have in our beamline is actually beamline downstream from the monochromator. It is situated here, and it is a thin polymer window. Also, if we speak about why the beamline is so unique, we could say that at the beamline we don't have any radiation hatch, which actually in some case our advantage, but in some case also our disadvantage, and I will present it a little bit later. But let's start where actually we are in the ecosystem of SOLARIS. Here you can see the diagram of different beamlines, which is already constructed and installed or under the construction in SOLARIS. And as you can see here, ASTRA is working in a tender and touching the hard energy range of X-rays. And if you can see here, we're perfectly fit to the actually the flux, the range of maximum of synchrotron radiation which is produced by the bending magnet. And taking into account that the critical energy of SOLARIS bending magnet is around 2000 electron volt, we could say that the energy range in which we are working is perfectly fits to the possibilities of the bending magnet of SOLARIS. If we speak about the heart of our beamline, it is actually our double crystal monochromator, which was produced in Bonn University, and it is an old-fashioned monochromator. It is actually modified Lemonnier design monochromators, which were very popular in 1917s. But from my point of view, they actually make quite good job because they are quite compact. As I already told you, they allow us to work us in a high vacuum. And what does it mean? It means that we can easily open our monochromator, change the crystals which we have in our monochromator. Here actually you can see the crystals, this gray silicon crystals installed to the aluminium holders. And in order to change the silicon crystals, let's say to germanium 220 crystals, we just open our monochromator and put them close the monochromator, and we could operate within 1 hour. Why it is so important for us? Because as you can see, the angle range in which our monochromator works, it is between 15 and 62 degrees. And in order to achieve this energy range which we claim, we need to change the crystals in our monochromators. Definitely there is a solution to make it, let's say, on motorization, but then the cost of such kind of a monochromator will be, let's say, very high. In our case, we actually use our hands to change these crystals. And what also very important, in this construction of the monochromator, we don't have step motors inside which governs the movement of the crystals inside the monochromator. Actually, we have only one stepper motor which governs the movement of the first crystal, and the second crystal is connected mechanically to the movement of the first crystal. And when the first crystal is moving, the second crystal making a quite complicated movement via mechanical chain. And actually this type of solution allows us to measure at such kind of low angles and achieve such kind of low energies. Also, what I would like to say is that at our beamline we have an unfocused beam. Here you can see the representation of the beam, where the width is around 10 millimeter and the height is 1 millimeter. But definitely the size of the beam could be tuned by the slits which we have at our beamline. Speaking about this energy range in which we are working from 1 to 15 kilo electron volt via changing the crystals which I represented to you, we could cover almost the whole periodic table, where actually you can see we can measure absorption edges of such kind of important elements as sulfur, chlorine, phosphorus, and also 3D metals as iron, cobalt, and nickel. Also, if we would like to go for 4D and 5D elements, we actually could measure L edges of these elements, and if, for example, we're speaking about uranium or thorium, then we can measure M5 edges for these elements. Speaking about the end station at our beamline, it is also very simple. As you can see here on the slide, we have ionization chamber I0, which actually allows us to measure intensity of the beam after the monochromator before the sample. We have ionization chamber which allows us to investigate the intensity of the beam which is passing through the sample. Here we have a silicon drift detector which actually allows us to investigate the intensity of fluorescence radiation excited by the beam on the sample. And what is also important, as you can see here, all of the elements which we have here, they are closed, and we could keep the pressure in our end station, let's say in a low vacuum around 10 millibar up to atmospheric pressure. And it allows us to provide experiments in transmission mode, actually which is dedicated for materials where you have a higher concentration of the absorber, or in fluorescence mode where you have a low concentration, less than 5% of absorber in your materials. Then we are using fluorescence mode, and we could make such kind of experiments in a low vacuum or at atmospheric pressure, and it is also allows us to go to these low energies. And speaking about if it is an advantage or disadvantage when we do not have a radiation hatch, from one point of view it is disadvantage, because we should to keep everything, as I already told you, vacuum tight. We could not afford to ourselves to have a beam outside of the vacuum flanges. But and definitely it put a lot of limitations to what we can measure and what kind of a sample holders we could use, because everything should be fit to the sample chamber. Definitely we have different sample chambers at the beamline. This is the smallest one, we have a middle one, and we have the largest one where actually we can change between them. And also I would like to emphasize that we have acquired talented engineers, which allows us to produce different holders and systems, which allows our users, and as you can see, to provide quite sophisticated experiments, also operando or in situ. It means that under different temperature, pressure, in liquids, or for example under different voltages. If speaking about the program which we have at our beamline, we have our custom-made program made by our engineer. It is called ASTRA Libra, and taking into account that I'm let's say a window guy, I asked our engineer to produce something very simple, which you can use after a few hours of working at the beamline. And I definitely can say, when you come at the beamline and you work with us for 2 hours, you could become very familiar with the program which we use at our beamline. So let's now speak about the experiments which we made at the beamline and what kind of information you can get from these experiments. Let's start, for example, from such kind of interesting experiments which we made at copper KH. And actually the goal of this investigation was revealing of the molecular structure of copper phosphonate groups anchored to the silica mesoporous silica, which has pores around 15 nanometers. So inside this mesoporous silica, functional groups of copper phosphate was anchored, and the main goal was to investigate what actually is the structure, the local structure of copper atom in these molecules which anchored to this mesoporous silica. At first we measured XAS spectra for these samples, and using machine machine learning, we managed to actually fit 3 spectra corresponding to 3 different models where copper could be, and we choose these three models as the actual one to where copper could be. Then analysis of XAS spectra allows us to confirm that actually these models are were chosen properly, and taking into account that 2 of the models were very similar to each other, we make a fitting only using 2 of them, and here you can see the contribution of these two models, where in which actually copper, in which state copper could actually be. And this analysis allows us to understand what atoms and in what kind of a geometry and on what distances we have around our absorber. Another experiment, I think it will be quite interesting for some of you, because I saw that in your program you have a lot of very interesting presentations about perovskites. Here actually is a perovskite which is used for low temperature solid oxide cells, and where researchers from Gdańsk University, they annealed this perovskite at different temperatures, and actually they investigate how the crystal structure of and the local structure of these samples changing depend on the annealing temperature, and we helped to the researchers to investigate it. At first we make XAS analysis, which actually XAS is very sensitive to the local structure of the absorber. It means that we could understand what kind of ligands are connected to our absorber and what actually a geometry of these ligands connected to our absorber. And also using XAS spectra, we were able to investigate the electronic structure, basically oxidation state of cobalt atom in these perovskites, which was annealed under different temperatures. And as you can see that with annealing, the oxidation state of this of cobalt atom inside this perovskite increases. And later we provide XAS analysis, which allows us to understand how the first coordination shell of cobalt atom inside this perovskites changes under different temperature of annealing, and also we could investigate how the distances between the cobalt and oxygen atoms in the first coordination shell changes. And actually this is a very beautiful, what I like very much is the wavelet transform of XAS spectra could give you actually an overview how the distances of the atoms changes with annealing, and also how the sample from amorphous going to, let's say, more crystalline, where the structure is more pronounced. Another example which was realized at the Beamline is actually investigation of memristor devices based on nickel contained complexes. As you can see, such kind of nickel complexes could be quite complicated, and that is why I would say that XAS analysis is the only way to make a good analysis of such kind of complexes. First of all, we made a XAS analysis where we tried to understand the actual electronic structure of such kind of a nickel contained complexes, and also we made operando experiments where we connect potential difference to this device, and we investigate if something is changing if we change the potential to the on the device. Actually, according to our DFT calculations, there should no any changes, and happily we do not see anything on XAS spectra also. So I would say that the theory met the practice. Also, later on, using the analysis of XAS spectra, we managed to unravel the structure of such kind of nickel-contained complexes, and we can, let's say, unravel what is the distances between the nickel atom and the atoms in the first, second, and the third coordination shell, and also what is the number of these atoms in each of the shells. And the last but not least example which I would like to show you, it is actually was realized at in the tender energy range at antimony L3 absorption edge, and it was also realized in operando regime. It is means that we had a battery which actually mimic the battery CR2032, which we actually use in plenty of our applications, but we have Windows in this battery from both sides, and we actually penetrate with the X-rays to this battery and investigate how the local structure of antimony changes during the charging and discharging of such kind of a battery, where we have such kind of a complicated composite as an anode material, and as a cathode we had sodium. And investigating such spectra, we managed to understand what kind of processes of let's say alloying and appearing of a new phases of antimony during charging and discharging of this battery, and it actually proved that such kind of a material could be a really stable anode for future sodium ion batteries. If we speak about cooperation with industry, which we provided, the Beamline, this is a quite nice experiment where we got 3 samples. One of them, as it was written on the envelope, it was a sample of somebody's hairs. The sample number 2, it was somebody's hairs, but actually after heating. And the sample 3 was somebody's hairs after heating, but before heating, this person put a lotion on his or her hairs. And as you can see here, when you heat your hairs, cysteic acid appears in the hairs, which actually provide to the information that they could be partially damaged. And somehow using the lotion could decrease the amount of cysteic acid in the hairs. It means that this hairs was not so damaged as without the lotion. But from my point of view, the company should work a little bit more in order to decrease the amount of cysteic acid. So definitely do not protect you from destroying of your hair. So be very careful in this if you heat your hairs. Next, what I would like to present you that every time at our Beamline we develop something, we are not standing on one place in order to give as much service to our users. That is why only a few weeks ago we managed to combine tender XAS plus Raman spectroscopy at our Beamline. The idea was that definitely using X-rays we could investigate almost the full periodic table, but as I showed you, we could investigate starting from sodium to uranium, but we could not investigate carbon ligands connected to our absorbers, only not directly. But using Raman spectroscopy, we actually can investigate the structure of such kind of tails or ligands connected to our absorbers. And here you can see the overview how we realized it. This is our middle sample chamber. This is our fluorescence detector, and this is a Raman probe, which is actually connected to a Raman microscope, which is standing very close to our end station. And simultaneously we could measure XAS, X-ray absorption spectroscopy measurements, and provide also Raman spectroscopy measurements at one point at the same time. And is also what is important, this kind of a microscope, it is an independent device. It means that even if your sample gives a very small and not intense Raman signal, which could not be used for providing simultaneously Raman measurements, because as you can see, Raman signal is much less than infrared signal which you can make in infrared spectroscopy. That is why not every sample could be measured in such kind of a, let's say, a combination XAS plus Raman. But nevertheless, we can take this the same sample, put it under the microscope, and investigate its also vibrational structure. It means that when you measure at our beamline, we could provide you with the data from two spectroscopies, from Raman spectroscopy and XAS spectroscopy. And what is also very important, sometimes when you prepare your publication, the reviewers ask you, but how do you think and how could you prove that what actually you are measuring is a synchrotron, it is the same sample which you measure in your laboratory. So in order to help to our users to overcome such kind of a, let's say, question from the reviewers, when you come to our beamline, we could measure your sample and you can then compare Raman spectra which you can measure at your university, and then you can tell to every reviewer that actually this is actually the same sample which was measured in my laboratory. So, and in the end, as my conclusion, I would say that ASTRA is a quite compact beamline. It is a very simple beamline, and in the framework of SOLARIS Synchrotron, it is like a workhorse for users from Poland and neighboring countries. We, as you can see, continuously upgrade our end station, and we cooperate with our users. And definitely, if you have some ideas or ambitious ideas, and you would like to realize your project at our beamline, you're very welcome. And also, what is important, we are creating our internal database of reference data. It means that if you come to our beamline and you have some kind of a sample, but you didn't manage to organize a reference sample for your investigation, please don't be afraid. We have a really big, we already have acquired let's say big library of different reference data for different elements, and the politics of our beamline, it means that your data are your data, but when you're measuring reference samples, it is actually going to this library, and other users also can use them. So on this point, I would like to present you the team of ASTRA Beamline. Come to us. As you can see, you will see these smiling faces from Solaris. Here on the right side, you could see our German partners actually who help us a lot in developing of our beamline. And here you can see the founding father of our beamline, Professor Josef Horms from University of Bonn. And on this, I would like to thank you and waiting for your questions.
Oh, any questions? Yes.
Okay, thank you for the talk. So, as far as I understand, it is a good place to measure where impurity goes, or whether it goes to intercalated or it substituted, right?
In principle, yes, because if you provide any holes to your material, definitely the local structure of actually the probing absorber which we investigate will change, and electronic structure of it also will change, and it is quite easily to investigate. For example, let's say you have a catalysis. Let it be a palladium catalysis which you deposit on some kind of a carrier. Let's say this could be, I don't know, cobalt carrier with a palladium nanoparticles deposited on it. And during the catalysis, you have a shift of electrons from cobalt to palladium, and that is why the electronic density of electrons in palladium will change. And you definitely can probe it by just measuring Xane's spectra, where the intensity of a white line will decrease. And this is a very, let's say, simple analysis. Could give you information of electronic structure of your material if you put some holes or you add something to your material. Yes, definitely this is how we could help you.
Yeah, okay. So I do not know about catalysis, but in many cases, transition metal decarbonites or cooperates, iron-based superconductors, the impurities would go to different places, and it would be interesting. It would be maybe interesting to find out. And can you first about sample sizes? Which requirements of samples?
As I told, our beam is not focused, and in principle, we are working with the samples which size, let's say, around few millimeters. It means that if you are speaking about perovskites, yes, in most of the cases, it is powders. So it means that we could make a pellet, or we could put this powder on a Kapton tape. Actually, we are not limited. We are not limited by the size. It means that we just spread the powder on the Kapton tape. If we speak about some kind of layers, multi-layers, thin layers, it is definitely then the size of your sample should be at least 5 millimeters in order to have, let's say, not to cut the beam by the slits, and to have a good signal on the fluorescence detector, for example, if we are speaking about nano size multi-layers.
Okay, and another question, thank you. And another question about amorphicity, as you said. For example, we're interested in molybdenum radium to understand how amorphous is this alloy, which is also superconductor. And what do you think, comparing, let's say, to diffraction?
I would like to ask you a question. What kind of information you would like you will be able to get from molybdenum iridium compound if they are amorphous using diffraction? Nothing, yes. But you will be definitely interested what kind of a local structure of molybdenum you will have. And personally, I like to work with molybdenum because we are measuring L3 edge of molybdenum. This let's say 4D metals as niobium, molybdenum, they have a beautiful, let's say, dividing of the peaks in two, depend on what kind of a local environment you have, tetrahedral or octahedral. And actually, the distances between these two peaks, which you have on your spectra, and also the intensity of one to another will give you information if it is a octahedral, if it is a distorted octahedral, or it is a tetrahedral structure of molybdenum in your compounds.
Okay, thank you.
Thank you very much. So